Okay, so let's start. Not a lot of announcements today. You know that there's a midterm on Monday, and project proposals are due on Grade Scope this Friday. Any questions on these? Okay, so this is where we are. I mean, we talked about understanding why learning works, and the main results, in fact, that we got to last time was that we said in a realistic setting where you're going to learn, you may try to be consistent with the training data. Typically, you may not be able to be consistent, so a more realistic way is to ask, let's assume that I've made some error training of H on my training data. Can I say something about the true error? What's going to happen in the future? And basically what we concluded is that we can bound it. So this is a generalization of the results that we saw at the beginning, where we assume that we are completely consistent. When we are completely consistent, what is this error? If you have a consistent learner, you've seen M examples. During training, you manage to be completely consistent. So what is the value of this? 0. So in the ideal case, perhaps this is going to be 0. In general, it's not going to be 0. Nevertheless, we said that the true error is going to be bounded by whatever you see empirically, plus something, and this something depends on M, the number of examples. And it should make sense to you that as M grows, the gap between what you see empirically, the observed error, and what you see in the future goes down. It depends on the confidence within which you want this to happen, 1 over delta. If you want to be very confident, you will have to pay to account for it by taking more examples. And it depends on the size, the log of the size of the hypothesis space. So that's that's really the important component of something that you have no control on. You already chose a hypothesis space on generalization. So we saw it this way as a gap in the error. And basically, it's important to see that you kind of have seen this structure before, and we'll see it again. Basically, the true error here is a sum of two components. One of them is the error on the training data, and one of them is, you can think about the generalization component, which is a function of the hypothesis space size. And we can rewrite this expression in a different way just by saying how many examples do you need to see if you want to make sure that your error, your true error, is bounded by epsilon. And essentially, algebra from the previous one is going to give us that if you want, with confidence, at least 1 minus delta, to have error less than epsilon, this is the number of examples you want to see. And again, this is a loose bound, but the important thing is what we see here is that, epsilon and delta are constant that you choose. You want to know what error you want to have, or you want to determine what error you want to have and what confidence. So everything depends on the log of the size of the hypothesis space. Yeah?
Can you go over what H is?
What is H? Yeah? The hypothesis space, which means the set of all functions your learning algorithm can consider. So this could be the set of all linear functions, maybe the set of all linear functions with some thickness, maybe the set of all monotone conjunctions, or any other hypothesis space that you want to consider. Okay, so that answered one question that we asked last time, the question of, realistically, in the case where my algorithm is going to make some error during training, is not going to be completely consistent with the training data, can I say something still about what's going to happen in the future? And this is the answer here. And we wrote it in two ways. The next question that we ask is, here H is finite. I want to generalize it to the case where H is infinite, because being a finite hypothesis space is too limited, and we want to generalize it. And we played with this example of rectangle, and I basically ask you, I told you I'm going to give you examples. I know that it's coming from a rectangle. What does that mean? It means that there are two dimensions, x and y, and the positive examples are within some rectangle. So there is a range of x's and a range of y's. And if your example is within this range, it's a positive example, otherwise it's negative. Something like this. And I ask you, can you learn this? And you developed an ad hoc algorithm. So you don't need to resort to any of the algorithmic tools we used before. It's very simple. You can develop a learning algorithm. And we agree that we can do it. However, the theory that we gave before doesn't apply. You don't know how well it's going to do in the future because there are infinitely many rectangles. So what we want to develop today is a theory that will allow us to say something in general, also for infinite hypothesis spaces. Now, the intuition is that when I tell you that something, your concept class is a collection of rectangles, it's infinite, but it's still smaller than, say, up to 17 sides convex polygons, or all convex polygons. So even in the infinite case, there are expressive classes and more expressive classes, right? You can think about linear threshold functions, which split the space to two spaces, or a conjunctions of these, right? So if it's a conjunction, you can think about it something like this. I have a linear space here, I have a linear space here, and their conjunction, which is going to give me some kind of a cone in the space, is where the positive examples are. So this is a more expressive class of function than just one half space. So even when I have infinite spaces, some can be more expressive than others. So basically what we're trying to do is to develop a measure of expressiveness for infinite hypothesis spaces. And the measure is going to be called the VC dimension for Vapnik-Chervonenkis dimension. So this is a combinatorial measure that was developed in the 70s or 80s. And it's going to be completely analogous to the size of H. Instead of counting how many hypotheses are there in capital H, we're going to compute the VC dimension of H. Okay, so the key idea there is the idea of shattering a set of points. So here we have a set of points. In order to understand the notion of shattering, we can think about this set of points and say, if this is our data, we can split it. We can define many functions on it, many Boolean functions. I can take some of these points and say they are positive. I can take the second part and say they are negative. And I can do this in many, many different ways, right? For each way in which I'm splitting it to positive and negative, I need a function that will agree with this split. And the question is, as a function of the number of points that I have, how expressive class of function do I need to agree with this split? So before we get to these many points here, let's start with 2 points. So if I have 2 points, I can definitely split them with a linear classifier, right? I can split them if I say that the top one is positive and the bottom one is negative. I can also say the other way around. I can say that the bottom one is positive and the top one is negative. And in fact, there are 2 other ways I can do it when I have 2 points. I can say that both of them are positive. I can say that both of them are negative, right? These are the 4 options that I have when I have 2 points. And all these I can realize with a linear function. Agreed? Now, so 4 options. I don't show you all of them. Now, if I have these many points, going back to these, I can split it this way. You can see the 2 colors, I hope. And if I do it this way, I can use a linear function to realize this, this split. But if I do it this way, I change the colors, as you can see. A linear function will probably not do it. I'm going to try a few. Not going to work with a linear function. I need a more expressive function, maybe something like this. So this is where you get an intuition for the notion of expressivity. With 2 points, linear function is going to do everything. With these many points, for some ways of splitting it to positive and negative, linear functions are not going to do it. I need a more expressive set of functions. And this is where the notion of shattering comes in. I'm going to say that a set of examples, like the one that you see here, is shattered by a set of functions if every partition of the examples into positive and negative can be realized by a function in H. So as you can see, the larger the number of points, the more expressive class of functions I need, because there's a lot more way to split it to positive and negative. So let's just define it again. So we say that a set, this is the same definition I had before. I'm talking about shattering a set of points, a set of examples, by a set of functions. And I said that this holds if every partition of these examples into 2 sets, positive and negative, can be realized by some member of this class of functions. Okay, so let's take some examples. We're going to carry this definition with us for a little bit. So here is a set of functions. So my set of function is left-bounded intervals on the real axis. So it's parameterized by the number a. Everything, the interval is from 0 to a for some real number a. So let's think about, so this is a class of function, right? It's an infinite class of functions, parameterized by a. How many points can I shatter with it? Suggestions? What about 1 point? If you give me a point, it can be positive or negative. I can shatter it with it. So let's say the point is 5. The point x equal 5. If you want to make it positive with this class of function, what will you do? You'll choose a equal 7. If you want to make it negative, you'll choose a equal 3. And this way, you showed me that the point x equal 5 can be whatever you want with this. What about 2 points? So this is the concept class. What about if I give you 2 points? Can you shatter it with this class of functions? Why not?
Because the positive one always has to be less than the negative, or the negative case.
Right, so basically, 2 points, I have 4 options of labeling plus and minus, right? So if I choose both of them positive, I can do it. I can choose a to be larger than both points. Let's assume that the points that I have are 4 and 5. I'll choose a to be 7. If I want both of them to be negative, I can also do it. If I want one to be positive and one to be negative, if I choose 4 to be positive and 5 to be negative, I can do it by choosing a to be 4.5. But if I choose the other way around, 4 to be negative and 5 to be positive, there is no function in this class of functions that can realize this labeling. Everyone agrees? Right? So this is the case that is going to bother us. So sets of 2 points cannot be shattered. As I said, some combinations of 2 points, some labeling can, but my definition is that I want to be able to find a function that agrees with any way of splitting the points. So if I have 2 points, I have 4 options, and for one of these labeling, no function in this class can realize it. Yeah?
Is it worth something that this class of functions can do 3 out of 4 possible?
No, not according to this definition. So this definition is all or nothing, right? So I should be able to realize all splits. But that's an important point because we're going to see the quantifiers are really important here. Okay, so let's move to a more expressive class of functions. We're going to move to intervals on the real axis. So a, b. So now I have 2 parameters to this function. It looks like this. Positive examples are between a and b. Negative examples are outside a and outside b. And I can ask again the question. 1 point, you can see that you can shatter. 2 points, you can also shatter. What about 3 points? What will be the problem? 3 points means how many configurations of labelings? 8 ways, right? So if I have 3 points, I can make all of them positive. I can make 1 positive in 3 ways. I can make 2 positives in 3 ways, and I can make all negatives, right? Altogether, I have 8 options. Can it be shattered by this class of functions? Why not? Someone there said no. Oh. No, I can make the middle point. Right, the configuration where the middle one is negative and the other 2 are positive, I cannot shatter. I cannot realize with a function in this class. Everyone agrees? And therefore, again, it's 1 out of 8, but this configuration cannot be realized, and therefore this class of function doesn't shatter it. Yes?
But this is all only in one dimension, right?
This is in 1 dimension. So I'm talking about now very simple class of functions. Nevertheless, they're infinite class of functions. Yes, so we just want to understand the definition of what shattering means. We can apply it later on for other classes of functions. Okay, so this is a set of functions. First of all, we want to make sure that we agree. And we also agree that all sets of 1 or 2 points can be shattered, but some sets of 3 points, for example, if I unify 2 of the points and make them the same, that's an uninteresting case. But sets of 3 points cannot be shattered. We're moving away from 1 dimension, so let's think about half spaces. We're getting to linear functions, but let's keep it in the 2-dimensional space now. So this is the picture. So one side of the hyperplane is positive, the other side is negative. Again, let's think about it. So I think you would agree that if you take 1 point, if you take 2 points, if you take 3 points, what happens? Can you shatter 3 points?
No, if they are all in a line.
If the 3 points are in a line, I cannot shatter it. Why?
Because if you have positive, negative, positive, then you can't separate.
Right. So if you have 3 points on a line and you alternate the labels, negative, positive, negative, no linear function will be able to realize it, right? So some configuration of 3 points cannot be shattered. But notice the quantifiers here. So I have a lot of sets of 3 points. Some sets of 3 points cannot be shattered, but some sets of 3 points can be shattered. So I can take just 3 points in a general position, not on one line. These sets of 3 points can be shattered. Agreed? So again, in order to show it, you have to consider 8 cases. You have to label the all 8 cases and to show a linear function in each case. So there are some 3 points that I can shatter, which means some 3 points that all their labelings can be covered by half spaces in the plane. What about 4 points? So 4 points, I would argue no configuration, no 4 points can be shattered. Why? Anyone wants to offer an argument?
You can have the exclusive OR situation.
But notice, you're right, but I'm saying no configuration of 4 points. No set of 4 points can be shattered.
Because if we alternate, one of the other point will be there.
Right, so something like this, we have to make it a little bit more, in a more subtle way. So first of all, I'm putting the quantifier. So for 3 points, there are sets of 3 points that can be shattered, which means all their configurations can be realized with this. But no set of 4 points can be shattered, and you can think about the 4 points and generate a convex polygon on them. So in this case, 1 point will be inside the polygon, and I'm going to make sure that it's labeled positive and all the others are labeled negative. And I will not be able to separate it with a linear function. So again, notice the quantifiers. Give me any set of 4 points. Now, what if I cannot generate a convex polygon? What does that mean? It means that 3 of them are on a line. And if 3 of them are on the line, you already agreed even before that I cannot shatter it. So basically, I covered all the cases. So, okay, so these were just examples. We gave example of 3 different classes of functions, vary by expressivity. The first one, the one-sided interval, could shatter only 1 point, couldn't shatter 2. The second one, the intervals, could shatter 2, could not shatter 3. The half spaces could shatter 3 points, at least some sets of 3 points, but no set of 4 points. And this leads us to the notion of VC dimension. Basically, VC dimension will depend on how large a set of points can be shattered. Before we get to the definition, I want to say something general. So if you have an unbiased hypothesis space, by unbiased here I mean everything is there, right? All functions are there. Then I can shatter everything, right? Basically, that's the definition. All functions are there. Every collection of points and can be shattered. The larger the subset of X, the larger the collection of points that I can shatter, the more functions I need, the more expressive the hypothesis space is going to be. And this is where the definition of VC dimension is coming from. So VC dimension is going to be a property of the hypothesis space. Again, I'm keeping here the definition of shatter, so we'll compare it. And given that, the VC dimension of a space is the size of the largest finite subset of X that is shattered. Okay? So let's go back to the examples that we covered. And again, quantifiers are important. Even if only one subset of this size does it, I already counted this shatter, right? And we'll see these examples. So what does it mean that we're talking about the largest finite subset of X? It means that if I want to show that the VC dimension is D, it means that I need to show that there exists a subset of size D that can be shattered, but there is no subset of size D plus 1 that can be shattered. Okay? These two together will make it equal to D. Okay? That's just spelling out the definition, right? So the largest finite subset of X that can be shattered can be spelled out by these two conditions. Okay, so let's try our examples. We started with half spaces. We said that no subset of size 2 can be shattered. And therefore, but we found subsets, in fact, all of them, but it's sufficient to say that we found subset of size 1 that can be shattered, and then therefore the VC dimension of half intervals, 0a, is 1. In the case of intervals, we show that no subset of size 3 can be shattered. That's the second condition here. We also found subset of size 2 that can be shattered, and therefore the VC dimension is 2. Half spaces in the plane, we show that no subset of size 4 can be shattered. It's true that not all subsets of size 3 can be shattered, but we don't care about it. We care only about the fact that there is a set of size 3 that can be shattered, and we show that there is the case when they are not on the same line, and therefore the VC dimension of half spaces is 3. Okay? So that's basically the definition. Again, notice that the quantifiers are important. In the case of 1 and 2, it was trivial. We didn't really need to be careful about the quantifier. In the case of 3, we should be careful because some sets of size 3 are not shattered, but it's sufficient that there exists, the first condition here, sufficient that there exists a subset of size D that can be shattered, and we saw that this happens for the case of 3. Questions? Yeah.
It seems like it's kind of an upper bound on complexity over X. Basically saying like if you're testing as if X is like the most complicated X, whereas if X were kind of more simply organized, the number of points could matter less than the BC. Meaning like if X itself, if there were 10 points, but really the hidden function is generating them well spaced apart from one another, your BC dimension could be very low, but the actual necessary hypothesis space to separate it might not be that big.
Okay, so I think your intuition is right, but the terminology that you're using isn't. So X is just the set of examples that I have, right? So I can consider any subset of points in X has nothing to do with the function class, right? It's just examples. What we care about is what functions are we defining over X, right? And there the complexity comes in. On the same line, I can define simple functions and more complex functions. For example, I can define half intervals. I can define intervals. Can you give me a more complex function class over the line? 2 intervals, sets of 2 intervals, right? So this is a more complex class of functions. And now, perhaps the VC dimension is going to be larger, right? Because with 1 intervals, we said that the VC dimension of 2, because when you looked at 3 points, you couldn't shatter them. Maybe with sets of 2 intervals, you will be able to do it. And you can define a set of K intervals. Put them wherever you want on the line. So X is the same. The class of functions defined over H can be simple, can be more complex. And this is where the expressivity comes in. So, and the idea is that you have the intuition that a class of 2 intervals is more expressive than a class of functions where the positive examples lie within any of these 2 intervals is more expressive than the class of functions where the positive examples are within 1 interval. And this is basically just a way to measure it. So, okay, so why is this important? It's important, and I'm not going to prove it, is because we can measure generalization as a function of VC dimension. So, and in fact, the functional form of what we can say is identical to the functional form of what we said last time when we talked about finite hypothesis class. We can say that given a sample of M examples, if we manage to find some hypothesis H that is consistent with M examples, where M is such, and we'll go back to the such in a second, then you are guaranteed that everything is going to be fine. Which means with probability at least 1 minus delta, with confidence at least 1 minus delta, the error of this hypothesis in the future is going to be less than epsilon. All right, so this is the consistent hypothesis case. There's a variation of it for the almost consistent hypothesis space also, as we saw in the other case. But the important thing that I wanted to highlight is that basically we have some constants here. And what we care about is that we have something that is a function of 1 over epsilon, as we expect, right? So if you want a smaller error, you're going to pay with more examples. We see 1 over delta or log 1 over delta, which also makes sense. And it's linear. The number of examples you need to see is linear with the VC dimension. Before it was linear with log of size of H. Now it's linear with the VC dimension. So VC dimension replaces the log of H in the general case. And that's where the importance here. So again, as we said before, the expressivity of the hypothesis space determines learnability, right? Given that in the PAC definition, what we care about is that this is going to be, M is going to be small enough, polynomial. Basically, it is determined by the VC dimension of the hypothesis space. Okay, so now, kind of to understand what we are doing here, VC dimension was, we just defined it, we defined it in general, right? For any function class. I didn't insist on H being infinite. It's a tool to deal with infinite function classes, but the same definition would hold also if it's finite. So let's just think about it. What happens if it is finite? Just to get a better understanding of what is VC dimension and what's the relation to the size of the function. What can I say about the VC dimension of H if it's finite? Any ideas?
Probably the max over the VC dimension of all individual functions in it.
What do you mean individual functions?
Is VC dimension defined for individual functions?
Let's see. That's actually a very, very good point. So let's see. What is VC dimension defined for? A class of functions. So for a given function, I don't know what is the VC dimension. It's really for a class of function. Again, why? Because you give me a set of points, and for this set of points, there are ways of labeling it, and each way of labeling it requires a different function, right? Because if I label this example in one labeling positive and in another labeling negative, I need a different function. Therefore, it has to be defined for a class of functions, not for a single function, okay? And the question is, how many functions do I need, or what's the expressivity of this class of function? And this is exactly what's measured by the VC dimension. Okay, so now that you remember this definition, let's go and ask the question, what happens if H is finite? So let's take a concrete case. I have K examples, okay? What does it mean that the VC dimension is M? I have K examples. Yes?
I guess that would mean that you found a class of functions that can partition or shatter K examples, but could not shatter K plus 1 for any permutation of positive negative.
Right. And what does it mean that it could shatter these K examples? Can you say something about the size of this class of functions? K examples. I can label it many ways. How many ways can I label it? 2 to the K, right? Because I have K examples here. We played this game a few times in other contexts, but it's the same game. I can take a subset and say, these are my positives, the rest are negative, right? If I have K examples, I can do this in 2 to the K ways, right? And because I can do this in 2 to the K ways, if I can shatter it, how many functions do I have? At least 2 to the K, right? Because each labeling is a different function, right? Because they are different, right? So at least on one example, they are different, so I need a different function. So if I assume that H shatters K examples, it must be that the size of it is greater than 2 to the K. Everyone agrees with that? The log of it, therefore, must be greater than the VC dimension of H. Okay? So basically, we made a connection here between the log of size of H, which was our complexity parameters on Monday, and the VC dimension, which is our complexity parameter today. And they are very related. Okay? And okay, so now that we played with it, you know everything you need to know on VC dimension. Who cares? Right? So the who cares comes from the definition of back learning, right? Because I promised you that learnability depends on VC dimension. So let's go back to our axis parallel rectangles that we looked at before and ask, can we pack learn it? And as we said, pack learning depends on two things. It depends on sample complexity, and it depends on our ability to come up with an algorithm given the M examples determined by the sample complexity. Right? So let's start with sample complexity. For sample complexity, we need the bound that we saw here says, oh, look at the VC dimension, and this will tell you how many examples you need to look at. So what is the VC dimension of rectangles? The class of axis parallel rectangles in the plane. So again, we can draw this. We already played with a few examples. This is one more example. And you know what you need to ask yourself, right? You need to ask yourself, if I take 1 point, can I shatter it with rectangles? Easy, right? So if it's a positive example, put a rectangle around it. If it's a negative example, put it on the side. 2, easy. 3, sum, excellent. Because if it's, for example, on a line, you cannot find a rectangle that shatters it, right? So if the 3 points are on a line, and you will have positive, negative, positive, oh, you can actually do this. What can't you do if it's on the line? Positive, negative, positive, you cannot do. Negative, positive, negative, you can do. Okay, because you just put a rectangle such that the positive is in the middle and the 2 negatives are outside. So 3, there is, if it's a general configuration, you can do it. What about 4? Again, you can do sum. And again, you can think about the case that if it's on a line and you alternate the labels, you will not be able to do it. But if you put 4 in a general configuration, you can place rectangles around, and you have to do it 16 different ways, right? 4 points, 16 different labelings, all positive, all negative, 1 positive, the rest negative, 2 positives, and so on. But you should be able to convince yourself that all the 16 configurations of 4 points in general position you can do. Yeah.
What if you were to just have a perfect square? How would you get the diagonals?
First of all, I didn't say that every configuration, right? We need one configuration. I will not put it in a perfect square. It will be simpler. Okay? So what you have to convince yourself is that there is a set of 4 points that all its 16 labeling are realizable with rectangles, with axis parallel rectangles. And I think that's something that, you know, in a couple of minutes of pencil and on a paper you can do. What about 5? Why not? Okay, so first of all, we convince ourselves that the VC dimension is at least 4, right? So far. And indeed, I agree with you, no set of 5 points will be realizable, and we have to give an argument for that. Suggestions? So again, we can go with a similar argument. Okay, so I'm just, before that, just to make sure that we understand that in order to show that VC dimension of H is at least 4, greater or equal to 4, it's okay that some sets of 4 points cannot be shattered, like this one here. But what I need is that some of them are. And in the case of 5 is trickier. I'm arguing that no 5 instances can be shattered. And to think about it, this actually is a good picture for that. We can think about the convex hull of the points. So there could be 2 cases. The 5th point could be inside it, or it could be on the side. Either way, what will happen? Let's take this picture, right? So I generate the convex hull. I'm arguing that the 5th point is going to be inside it. Then
If the 5th point, the point inside is negative and all the others are positive, that's not possible.
right. So this labeling of positive outside, negative inside, cannot be realized with an axis parallel rectangle, and therefore no set of 5 points can be shattered. Right? So this is basically the argument here, and together with what we've showed in the previous slide, we proved that the VC dimension of 4 is 4. This guarantees pack learnability, right? So the reason we did this is because we wanted to show that the VC dimension is small, and therefore, sample complexity-wise, it guarantees pack learnability if we have an algorithm, right? So we need an algorithm. But we do have an algorithm, right? So we talked about an algorithm last time. Let's just go back to it. What would be a learning algorithm? So I'm giving you points. I told you it's coming from an axis parallel rectangle. Give me an algorithm, which means return an axis parallel rectangle. Now remember that it's not going to be useful if you give me a neural network that does it. Not here at least. Because my hypothesis space here, the hypothesis space for which we made the pack learnability argument is axis parallel rectangle. So you need to work with this hypothesis space. Don't invent another hypothesis space. Right? So with this hypothesis space, what would be an algorithm? Yeah.
Are we assuming that the points are such that there exists some learning algorithm which will be consistent on all different points?
So the game we're playing here is yes, right? So I'm showing you that it's consistent. As we showed in the bounds, it doesn't have to be, right? But now I'm kind of running through the consistent hypothesis case. Give me a learning algorithm that returns something consistent. I know it's going to be pack learnable if the sample complexity is small enough. So what would be a learning algorithm here? Right, so we discussed this last time. I'm giving you positive example and negative examples. Because I told you that it's coming from an axis parallel rectangle, which means there exists an axis parallel rectangle that separates the positive and the negative, and therefore I can just look at the positive. I'm going to take the max and the mean over the x-axis. I'm going to take the max and the mean over the y-axis, which means I'm containing in this box that I define all the positive examples. None of the negative example can be there by definition. And that's a hypothesis in this space that is consistent with the data. Agreed? Okay, so that's, and we prove that it's axis parallel, the class of axis parallel rectangle, functions that are axis parallel rectangles are, in fact, we prove not only that they are pack learnable, we prove that they are efficiently pack learnable because all we had to do is to touch each point once, it's an efficient algorithm. Now, by the way, if I were to give it to you in practice, and this would be the data, and you need to return to give me a learning algorithm, would that be the hypothesis you return, or would you do something else? Yeah.
The only risk with that is if there's a point slightly outside the rectangle, that's positive, we would classify it as negative. So maybe instead of putting the bounds as the max positive point, you put it halfway between the max positive and the min negative.
Right. Any argument with this argument? Right. So in practice, I showed you that I can find something consistent, but it's a very sensitive algorithm, right? Sensitive to any fluctuations of the example. So it's probably more realistic and better to look at the positive container, and at the same time, look at the negative around you and minimize the margin to this, right? It's exactly the same idea of minimizing margin when you have a linear separator that we're going to revisit next week. But basically, that's what you want to do, right? So you want somehow to be a little bit more flexible. So that's what you'll do in practice. Okay. Questions so far? Yeah.
Suppose the data wasn't consistent. It's not trivial to come up with an algorithm which will backlearn, which will give the backlearnability bound, right?
The algorithm is going to be a little bit more sophisticated because you will have to decide, what do I do with outliers, right? So if I tell you, for example, if I give you some bound, or you can assume that you have some bound on the number of Mills classifications, then you can do it, right? So I give you data, and I tell you, 5% of the data is noisy. So you will try to find the best rectangle, giving up on no more than 5% of the data. The algorithm is going to be a little bit more sophisticated because just think about it. Let's assume I add one positive example, and it could be here, right? So first of all, you will recognize easily that there is noise in the data. And then you'll have to decide what to do with it and how much to give up. Yeah. So the algorithm is going to be a little bit harder. Yeah.
So what are the formal criteria for backlearnability?
Okay, so let's go back to it. So what are the formal criteria for backlearnability? So the definition calls for sample complexity and the existence of an algorithm. That's it, right? So we can go back to our definition. In fact, no, I will not go back to the definition. I will go back to the consistent hypothesis that we kind of end up with last time. Okay. So backlearnability, by definition, calls for it's learnable if there is a learning algorithm that has the guarantees with probability at least 1 minus delta. It's going to make error less than epsilon, where it observes m examples where m is polynomial in the complexity parameters. However, we don't need to always go back to this because we already showed with the Occam's razor result that if you are consistent with m examples, this addresses your question about consistency. So in principle, I don't need to be consistent. All I need is to find some hypothesis that I can show with confidence 1 minus delta as error less than epsilon. In practice, we show that if you happen to be consistent on m examples, this 1 minus delta epsilon condition is going to be satisfied. And therefore, we reduce the burden of proving pack learnability to this. Draw a sample of size m, develop an algorithm that is consistent with it. If m is small enough, everything is going to be good and you'll be pack learning. Everything will be good, which means with confidence at least 1 minus data, the error in the future is going to be less than epsilon, and therefore you satisfy the definition of pack learnability. And if your concept, if your collection of examples M is small enough, you're done. So that's what we did actually when we did KCNF. We said, it's going to be very difficult for us if you give me a KCNF to directly prove on this 1 minus delta epsilon condition. Instead, I'm going to resort to my Occam's razor result, and I'm going to show that, 1, I can develop an algorithm. 2, the number of examples I need to run these algorithms on is polynomial in the complexity parameter. And that's what we showed last time for KCNF, right? The way we did it is the sample complexity was just an outcome of counting how large is H, how large is the class of KCNF. We showed that it's small enough. Log of the size of KCNF was polynomial in N. And then we developed an algorithm that knows how to return a KCNF that is consistent. The same thing we did now with rectangles. We said we are relying on this, on the result, on this result basically. No, I need the result with the VC dimension. So. Okay, we are relying on this result that says if you take at least this many examples, it's going to be okay, which means the hypothesis that you will get, the one that is consistent with these many examples, is going to have small error, less than epsilon, with high probability. Right? So that's the PEC condition. And therefore, all we have to do in order to prove PEC learnability is to show an algorithm that is consistent with M examples, 1. 2, show that M is small enough, which really depends on showing the VC dimension is small. Answers your question? Okay, questions on this? Is this clear? So really what we've done is this. We have a definition. The definition says you have to show me that you managed to learn a good hypothesis. Good, by good I mean 1 minus delta epsilon condition. That's often hard to do directly, to run the algorithm and prove something on the algorithm. Instead, we said, we proved in general an Occam's razor theorem. This is an instance of the Occam's razor where VC dimension replaces H. We proved this theorem, and this theorem says, really all you have to do is to find an algorithm that is consistent with your examples, and the 1 minus delta epsilon condition will be satisfied. You don't need to prove this directly. It comes directly from, it comes from the theorem and the fact that your hypothesis was consistent. And now you have to worry about the sample complexity, right? So if you've done this with a hypothesis class that is way too large, not going to do it. If the hypothesis class is small enough, it's sufficient, yes?
So when you say draw sample size M, is that for any M or for a specific M that you
For this M. M is to be at least this large, and now the 1 minus delta epsilon condition is going to be satisfied.
Gotcha. So you're actually picking epsilons and deltas, getting your M, finding an algorithm that is consistent with it, and then you get it.
Yeah. So you, So really, the PEC definition says that you have to be polynomial in epsilon and delta. M has to be polynomial in epsilon and delta. And that your hypothesis has to be epsilon delta good, let's call it. This theorem says if you take as at least these many examples, you are epsilon delta good. Okay? So you tell me what epsilon delta you want. I want to have error less than 0.1. I want to have confidence at least 95%. So you gave me your epsilon and delta, and I tell you, okay, if you take as at least these many examples, the error is going to be less than 0.1 with confidence 0.95. So, which is what the definition calls for. Yes?
For the inconsistent definition of back-learnability,
Yeah.
there would also be an additional parameter, say alpha, which would say that if you're consistent on one minus alpha percentage of the m examples, then you're guaranteed the epsilon delta bound, right?
So actually, for the inconsistent, there are two options. One option is to directly prove that what you've learned is epsilon delta good, which is often hard to do. The other option is what we call the agnostic learning thing, and there's actually some subtlety in the agnostic learning. It's not sufficient to be alpha good on the empirical data. It actually has to be, for technical reasons of the proof, it has to be the best hypothesis that you can learn on this data has to be alpha good. So if you go to the way I stated the agnostic theorem, it has the best in it. So it's a little bit more subtle than just find one that is good. But in practice, maybe find one is good enough. It's just that there are technical difficulties in proving theorems. Other questions? Okay, so yes.
I mean, for the rectangular, how do you prove that the 5 points, there is no subset of 5 points that can be shattered? Because if the middle one is also positive, there is a 5 point and it can be shattered.
So what do I have to do in order to prove that the VC dimension is 4? I need to show that give me 5 points, any 5 points that you want. It's not possible to shatter them. 5 points means that I have to consider 32 ways of labeling them. It's enough for me that I show you one labeling that axis parallel rectangle cannot realize, and I'm done.
But in the VC definition, you mean that there is some subset you can shatter it. That's fine. It does not require all the subsets that you can shatter.
No. So let's get our quantifiers organized. So it's a subtle issue here. So in the shattering, what I need, you give me a set of points. To say that it's shattered, I need all the labelings of this set of points to be realized by my function class. Okay, that's shattering. Now, in the VC dimension, the way I'm using it is the VC dimension is going to be, let's go back to this, so it will be written. Here. Look at these two bullets here. If there exists a subset of size D that can be shattered, then the VC is at least D. And by can be shattered, I mean there is a subset of size D, all its labeling, all its 2 to the D labeling can be realized by my function class. And then the second bullet says, when you take a subset of size D plus 1, any subset, it cannot be shattered. What does it mean that it cannot be shattered? It means that out of the 2 to the d plus 1 configurations, out of the 2 to the d plus 1 labelings, at least one of them cannot be realized by my function class. Okay, so the quantifiers are really important here. Let's go back to rectangles. Rectangles, I showed you, for example, I showed you a set of 4 points, d equal 4, the general position 4, that can be shattered. I looked at all 16 labelings, and I said all of them can be realized with rectangles. Everyone agrees on that?
May I ask if the 4 points are positive, negative, positive?
If there exists a subset of size 4. Right? So I took the 4 to be something like this. These 4 points. I can take any labeling that you want. All positive, all negative, 1 positive, 1 negative, 2 positive, 2 negatives, any configuration, 16 possible configurations, and I can all realize them with rectangles. That is sufficient. This is that there exists a subset of size D. Of course, there are also, if you take these points as your 4 points, I cannot shatter it. But I don't care about this, because the condition says there exists. So I found a set of 4 points that all its 16 labelings can be realized with rectangles. That is sufficient for the first bullet. Okay? Now I'm taking 5 points, and I'm arguing that any set of 5 points, doesn't matter how you put them. You can put them on a line, you can put them any set of 5 points, a given set of 5 points cannot be shattered. What does it mean cannot be shattered? Again, the quantifiers are important. So now I have to consider 32 different labelings, and it's sufficient that one of them cannot be realized to say you cannot shatter it. And that's what we showed here, where we said, take your favorite 5-point set, a general 5-point, because I'm going to make an argument for any set of 5 points. At least one of the labelings, out of the 32 labelings, cannot be realized with axis parallel rectangles, and therefore the VC dimension is strictly less than 5. Okay?
So the subset here means the different arrangement of the points, right?
The labelings are the different arrangements, yes. So this will be plus, this will be minus, plus, minus, plus.
Arrangement and use the different position of the points.
So as I said, for the 5 points, I don't care where they are. It should be for any. So the quantifiers here are subtle. You should all look at it more carefully and kind of convince yourself that you understand it. So there's a for all, and there exists here, and you have to really get where it is. Yes?
So can you make the one step? So we found DCH is equal to 4. Great. We plug it in, we get our M. And now all we have to do is build an algorithm that's consistent for it, and we demonstrated it's pack learnable. But why is the fact that DCH is equal to 4 guarantee that?
In fact, it doesn't matter whether it's 4 or 7.
It just has to be finite.
Yes,
Okay.
it would have been fine, right? But we just can't compute that it's 4, so it's nice to compute that it's 4. Would have been 7, would have been as good for pack learnability. Okay, so let me just summarize what I wanted to say here. So basically, all this theory allows us to study learnability, to say there are conditions under which things will not be learnable. if your hypothesis space is way too large, basically. There are issues that are relevant to easiness of learning. And again, they depend on the hypothesis space. Now, it so happened that you can actually prove lower bound. You can actually show that, in fact, you have to see enough examples to learn. But all these lower bounds, frankly, are basically they're extreme cases, right? It basically means I can generate a distribution such that if I sample from this distribution and you don't take enough examples, you'll never be able to learn. So maybe it's a little bit less interesting in realistic cases, but it's good to know that, extreme cases exist and you have to be careful. So let me summarize what we've done. So basically, it's the first model. I mean, there's been a lot of development on top of it, but it's the first model that allows us to think quantitatively about effectiveness of learning algorithms. Basically, to understand what's important and what's less important. We realize that sample complexity is important, and it depends on the size of H, or equivalently on the VC dimension of H. We talked about the notion of computational complexity. I didn't elaborate on this so much. We just talked about the fact that we want the algorithm to also have small computational complexity or polynomial computational complexity. I gave some examples for the fact that some classes of functions are non-learnable. It doesn't matter what you want to do, what you will do algorithmically. In general, you cannot learn into this class of functions. Finite automata were one example, but there are many other interesting examples. And the key thing is that basically it gives us a way to link complexity of learning to various assumptions. There's many extensions of this. I mean, we can extend the model to learning with noisy data, learning from specific distribution, learning with somewhat different protocols, like learning with queries, teaching, active learning, and so on. There is an extension of PEC learning theory that also makes an assumption on the distribution over the hypothesis that your algorithm sees, because your algorithm typically doesn't look uniformly at the hypothesis, right? So if you think about your decision tree algorithm, it's a search in the hypothesis space, but it doesn't encounter each tree with the same probability. So it makes sense to assume some distribution, prior distribution over the hypothesis, and then mix PEC learnability with Bayesian theory. I'm not going to talk about it, but people that are interested could search for PEC Bayesian, and you'll get some theory there. One of the key issues that is significant in this theory that beyond just giving us a theoretical understanding of if you do this, it's going to be good in the future, which you always want, right? So if you build a bridge, you want to know what are the chances that cars of this weight can go over it. For the same price, if you learn something over data and you observe the error, you want to know what does it mean in the future. This theory also gave rise to interesting algorithmic possibilities. So for example, the notion of the Winnow algorithm was developed based on theoretical consideration, kind of looking at sparsity. And what we're going to do in the next, the notion of regularization, in fact, was developed in an ad hoc way before, but is explained via the theory of PEC learning. And the two algorithmic framework that we're going to, algorithms that we're going to talk about next, which are really important, support vector machines and boosting, are direct consequence of PEC learning. In fact, boosting started with a PEC learning question. We're going to talk about it in about 2 weeks. And support vector machine also came directly from VC dimension theory and trying to develop algorithm that minimizes VC dimension, basically. So the theory also had some practical significance beyond just understanding why learning works or when learning works. Final questions? Okay, so midterm exam, we probably managed to find another room. So some of you, and we'll send you emails, will be able to take the exam in another room. So this will sparsify this a little bit. Otherwise, it's going to be dense either way. But anyhow, we'll see you all on Monday, and have a good weekend. Yes.
Is there some algorithm that good at learning the sparse data, like the we know that the others are not good at this?
Say it again. I didn't get it.
I mean, is there a difference between like some algorithms are good at learning sparse data, but others are not?
Yes. So some algorithms are doing better for sparse data than others.
Why they are doing better?
Because they are designed to perform better in the case of. So I talked a little bit about we know. And I quoted some bounds. So we know is doing better on sparse data than other algorithms, for example. Why does it happen? Because the update rule is better for sparse data. The update rule is multiplicative. So I'm not sure what type of answer are you expecting. Do you want a proof, or do you want...
Why they can do better?
It's hard to explain in 2 seconds why. I mean, the proof of that is involved. But it really is due to the different update rules. The update rule determines, I mean, the update rule determines the behavior of the algorithm. Yeah.
So, quick question.
Yeah.
Is this lecture coming for the midterm?
Yes.
This one?
Yes.
One of the slides, I think there was a typo. Maybe I'll show it next time. In the JCNL thing,
Yes.
at the top you defined F as a conjunction over from 1 to R.
Yes.
But in the latter part, it's defined as M. So it's defined as the conjunction of C1 to M.
Oh, thanks.
It's not supposed to be M, right?
No, it should be R. Yeah. It was used to be M
Yeah,
also at the top, and I
exactly.
fixed it, and I didn't notice this one. Okay, thanks.
Jesus Christ.
Yep.
Shit. There you go. Check. Both of them are fucking... You want another one? Sure. You can plug in right here.
Oh, yeah, I mean, that's what, I mean, I hope that, I mean, I've been, what do you expect? You know him better,
Do you prefer, because I do have HDMI direct.
Oh, HDMI is nice, yeah. That's, a little bit nicer, yeah. Okay, you have privacy while you're getting ready.
Introduce myself. I'm a good friend. I'm Harvey Rubin from the School of Medicine with a secondary appointment here. So I've been pushing our guys, we need to do this. Because I do infectious disease, but we're really interested in the whole area of machine learning, AI, wearable devices, imaging in this thing. So I just sent my buddy here a set of slides about this very topic.
Yeah. Yes,
So-
so it's such a coincidence that we were talking about it last week and then we saw your.
So
So the third part of my talk would be really about using machine learning for infectious diseases and blood tests.
Great, perfect.
Yes. So you will have to just be patient to go through the math first, and then the infectious disease after.
I will get called out at the last minute because I'm in clinic this afternoon in infectious disease.
So roughly 12:30 to 12:45.
I'll be here
my
for that.
plan. Okay. All right, that's fine. Go for it.
Did they talk to you about the recording?
Yes.
So we're recording your slides and your voice, not your picture, not the blackboard.
All right.
Also, it's on a timer. We start at 12 noon. When that happens, when 12 noon comes around, I will turn the lights down a little bit.
Yeah.
That'll be the cue for your introduction.
Yes.
So,
Do you have a clicker?
clicker, no.
To advance the slides?
The department usually provides those. Let me see the transcript for a second. Yeah, okay, good. Are you ready for the slides to come up?
Yes. Does either of you have a clicker by any chance?
Oh.
I do not have a clicker.
Yeah, I think the ESE department has one.
Hey, Jim, how
are
you?
Welcome.
Good to see you.
We're hooking up with breakfast tomorrow. Yep. All right.
Perfect.
There it
Good
is.
to see you again.
Good to see you. How are you?
Yes. Amazing. I've seen you 3 times
Yeah, I
in
feel
1
lucky.
week.
Yeah. So we're going to be grabbing lunch tomorrow. Then.
Yes.
Forward to it. I'll click it on my side. Oh, I think that got to be one. The other way around.
Oh, yep.
The other way, huh?
It's always the third way you try.